Welcome again to our webcast today titled Bringing Order from Chaos, the Role of Analytics in Integrating Renewables, Distributed Generation, and Electric Vehicles into the Grid. Today you will hear from George Simons, the Director of Consulting and Analysis with Itron. George is responsible for providing utilities, industry, and government clients with expert services in the area of renewable and distributed generation program design, implementation, evaluation, and market assessment. George?
Good morning or good afternoon, depending on where you're at. And Becca, thank you. And I want to thank everybody for taking the time to join this webcast. So we are going to talk about analytics and the role in which it can play in helping to integrate distributed resources into the grid, some of the challenges and some of the opportunities associated with that. And to really put this into perspective, we live in a time of a changing energy world. And if you think about what's happened is that in the past 100 years, we've gone from an energy arena that was supplied largely by coal, oil, and natural gas. Customers relied solely on the utility for power, and the role of the customer was primarily just to purchase electricity from the grid. We also have seen quite a widespread adoption of transportation. In the U.S., in 1905, there were about 70,000 cars in the country. By 1915, that increased to about close to 2 million cars. By the end of 2014, we now have 1 billion cars worldwide, cars and trucks. But again, the biggest connection between transportation and the grid was that transportation increased oil prices. Things are changing now. So Becca, I'm not getting, let me see if this all, okay, so, well, it gave all of the animation all at once. But what we're seeing today is an emergence of renewable energy resources across the world and a lot of distributed generation. And within the U.S., we see that primarily in widespread adoption of rooftop PV. We're also at the same time seeing an introduction of smart technology, smart devices, and smart metering. And what that's led to is more sophisticated customers for the utilities. And these customers want more and they're demanding more from the utilities. And we're also seeing the emergence of electric vehicles that are tied to the grid. And from a demand perspective, this is important because electric vehicles can increase the demand in a household by as much as anywhere from 3 times up to 7 times the amount of peak demand. And so what does this portend to the future? So we know that there's, at this point in time, rapid growth in renewables. And if I just look at PV, we can see that from 1990, there's about 50 megawatts of PV being added every year. By the end of last year, that grew up to 50 gigawatts per year. And right now, market experts are anticipating that by 2020, the amount of PV we're going to see entering into the world is 500 gigawatts per year. So tremendous growth in PV. Tony Seba comes out of Stanford University. He's written a very interesting book called Clean Disruption of Energy and Transportation. And his contention is that we're in a time of very rapid change. And when Tony looks at electric vehicles, he's drawing the conclusion that by 2030, gasoline cars are going to go the way that horse carriages went in the last century. So tremendous amount of changes in our energy world. And in order to really understand these changes, we need to understand how the grid operates. So the conventional grid, I think everybody is well aware of, electricity was produced by central station facilities by the utility. The power flowed from the utility all the way down to the customers. The utility controlled the power quality, how it was delivered, and the costs. Customers, again, their primary role was simply to use energy and pay for energy. Under today's grid, that's changing by quite a bit. We have, at this point in time, new players providing generated electricity into the grid. Merchant facilities have been around for a while that sell directly to the utilities, but increasingly we see a number of merchant plants that are renewably powered. We also see commercial customers who have traditionally provided backup generation in the case of the grid going down. Increasing number of commercial customers are putting in renewable as well as distributed types of generation. And again, with rooftop PV, we're seeing residential customers now adding in generation to the grid. And again, we're seeing this at the same time occurring with smart technologies, smart metering, and new policies like net metering that's changing the grid landscape quite a bit. So we also know that distribution systems are becoming much more sophisticated. And if we look at distribution system operations, we know that there's a number of ways in which distribution engineers control power quality. One of the biggest issues for the distribution system is our voltage problems. And we see under and over voltages occurring, transient voltages that occur can last only seconds, and those can, again, turn as swells or sags. We see power flicker that can be caused by sudden and large increases in load current. And we also see phase imbalances, again, that occurs primarily with wind systems, but we're seeing it with other types of systems also. And in distribution systems, we're seeing the use of reclosers, capacitor banks to go ahead and control voltages. There's been a move towards automated distribution control, and again, most distribution engineers rely heavily on automated services. SCADA, supervisory control and distribution automation systems, administration systems, allow for signals to be transferred from between transformers, intelligent electronic devices. Those signals can be automated, so SCADA systems allow for remote control of different parts of the grid. In addition, AMI, Advanced Metering Infrastructure, smart meters, allow us to collect an immense amount of information about customer demand. And when we use those in combination, we can begin to see different ways in which we can control operations within the grid. One of the most prevalent examples right now is automated demand reduction. So before I go too much further, though, I want to talk about different types of distribution systems within, or different types of distribution systems within the grid. So radial systems are pretty prevalent, especially in rural areas. So loads are located along the line, moving out from the substation or the source of power, and located laterally along the line. Ring or loop systems are literally where you have service loops through the service area, ties back to the original source. It contains a substation and oftentimes some sort of alternate generation so that customers can be provided with power in either direction. So it increases reliability. Network systems are much more common in urban areas, and they're interlocking radial and loop systems, and they might have a number of generation sources within a network system. There can also be a number of substations. All three types of systems are found in the grid, but there's increasing importance of network systems. And not only do they tend to be where we see the most congestion right now, but they also provide an important pathway in how we can get better value out of integrating distributed resources into the grid. And so at this point in time, I'm going to switch over and talk about some of the challenges that distribution engineers face with adding PV into the grid. So to really understand this, this top chart is just some examples of different distribution feeders, commercial, industrial, residential. One of the most important facts here is that when we start talking about peak loading, a lot of folks have referred to a CAL-ISO system peak for California, the entire system peak, or the load profile for the entire system, or a system load for PG&E or Edison or whatever utility. But when you get down into the thousands and thousands of distribution feeders, you begin to recognize that each of these have a different profile. They peak at different times. There might be multiple peaks during the day, and there's different durations to those. And those are all impacted by what makes up the customer mix on the distribution feeder, what are the characteristics of the distribution feeder. And so when you start to think about distribution feeders, you have to recognize that every single one is different. So on the bottom left-hand portion of this chart, we're really looking now at just a typical PV generation profile. So what you see is PV tends to increase power output during the early part of the morning, peaks in the early afternoon, and then declines in the evening. And this is, again, a south-facing rather than a western-facing PV system. If you look at how that intertwines with customer demand, you might have a load profile, this blue dotted line here, that's typical of most residential homes. So there's not a lot of peaking in the during the day, but as people come home from work, load increases, demand increases. And the net impact of this is that what happens is PV is actually servicing the load at the site, and so you actually see a drop, what looks like an apparent drop in demand at the site. That's important to recognize that PV masks load, and that becomes important later on in this discussion. Another thing about PV is that, again, when you have a PV site, a PV generation system at a site might actually generate more power than what's being required at the site. You get what's called net export. And so you have power moving from PV systems on homes and commercial residents or commercial buildings out into the grid. And that has all sorts of implications because you can get reverse power flow. And so again, that can greatly impact what's happening in the distribution system. So let's talk a little bit about penetration of PV into distribution systems. So this figure up here on the left is, again, a radial, lateral type system radial, and you see some PV located out here on the branches. There's not a lot of PV. And so we talk about low versus high penetration PV. And in general, when we're talking about low PV, what people have tended to do is talk about when PV, when the combination of the PV generation capacity on a line is less than 15% of the peak demand loading on that distribution feeder. When we talk about higher penetration, we're really talking about where PV may constitute, up to 50% or more. And in many utilities now, we're beginning to see that they're either, in the case of Sacramento Municipal Utility District, they have PV capacity which exceeds 50% of the peak demand of the feeders. And in some cases, we know from studies by NREL and EPRI that utilities face much higher penetration levels going in the future. In Hawaii, I know that they're talking about 80% penetration in some cases. So what does this really mean when you start getting high penetration PV? So we got to remember that photovoltaics has different characteristics. Again, it's intermittent. It depends on the sun. It depends on other factors. But when you so EPRI has done some work on looking at the effects of high penetration PV on distribution feeders. There's a number of factors that get affected in distribution feeders by high PV penetration. There can, again, be voltage imbalances. There can be overvoltage. High penetration PV can increase the number of faults that occur on a distribution feeder. You can get unintentional islanding or sympathetic tripping that leads to unintentional islanding. You can run into power quality problems with total harmonic distortion as well as some individual harmonics, and you can run into thermal overloads. So one of the other key takeaways from some of the work that NREL and EPRI and some of the other utilities have found is that even though all of these factors can be occurring in distribution systems anyway, PV tends to exacerbate the problems. And where PV is located on a distribution feeder is important. The further out from a radial system, further out from a substation on a radial system, PV tends to cause bigger problems, as well as larger PV systems tend to have bigger problems than smaller PV systems. But again, there's a host of factors that go into this. EPRI's done some very interesting work on what they call hosting capacity to begin looking at how much PV could you actually add into the grid and not run into some of these reliability issues. So I mentioned that PV was intermittent. So the other thing to remember about PV systems is that when cloud cover comes over the PV system, whether it's a large utility scale system or it's a large number of small scale residential systems, you're going to have a decrease in power output from the PV system. This can be rapid, it can be of short duration or long duration. But as clouds pass overhead, again, PV generation output is going to drop. And remember earlier I mentioned the fact that PV actually masks load because at each of the sites, when we're talking about residential or commercial rooftops, because to the utility it looks like that demand has dropped. When the cloud cover comes overhead, all of a sudden that load shows up because the PV generation drops and the load may still be the same, so now the apparent load increases. For sites that are under automatic demand response control, this can have some very interesting consequences. This slide is simply some information from HECO, Hawaiian Electric Company, where again I mentioned they have very high penetration PV. And so the top part of the chart is showing PV generation and site load on a clear day, and then what happens when you have cloudy days. So again, very dramatic decrease in power output that can last for any length of time. PV is not the only distributed energy resources being added to the grid. We also have some natural gas power type distributed energy resources, whether those are microturbines, IC engines, fuel cells, or small gas turbines. Commercial as well as, in some cases, residential users have put these types of devices into their sites. We know that in California in particular, but I assume in most other places where there's rooftop PV, commercial and residential users are combining PV with residential storage or commercial storage. So the important point here, though, is that not only do you have PV entering into the distribution system, but you've got distributed generation and storage that's entering into these sites. In the case of DG systems, what's interesting is that in some of these cases they have they use natural gas, so they're not an intermittent resource. They can actually be available at any time during the day or night, and they also can ramp up fairly rapidly. So what we're seeing is emergence of DG, whether it's a host site deciding to put it in or a third-party provider who's going to provide some increased reliability to the host site. But these systems are beginning to emerge into the grid in combination with PV. Lastly, at the start of this webcast, I mentioned that we're going to see a greater increase in electric vehicles. And so what role does that play? So if you look at some typical residential profiles, what you expect to see is low demand in the morning, increasing demand during the day, some high demand in the evening, and then dropping off. Most folks who have a charging system at their home are going to charge at night. And so if you begin to look at what happens is that the demand gets pushed up. If you're charging with a slow charger from midnight to 6 a.m., the demand at the household is pushed up. Again, this can increase demand 2 to 3 to greater amounts depending on the type of charging system. So you begin to see differences in the load profile at homes. Now again, if you are talking about a large amount of PHEV within a distribution system, what that tends to do is, again, it pushes up the load profile on that distribution feeder. These can be occurring on branches within the distribution system, but the overall effect, again, is it's changing the load profile on the distribution feeder. So we now have PV systems. Didn't even mention wind. We've got wind system. We've got different types of distributed generation. We've got storage. we've got electric vehicles. And all of these are landing on the doorstep of the utility distribution engineer, sometimes at once, and it can be any number of systems that are entering onto their doorstep. So remember, this can be any combination, any location. It can be any magnitude. You can get PV systems or DG systems of any magnitude coming into the distribution system. So a lot of distribution engineers, for them, this appears as literally chaos. How to deal with this? You've also got the backdrop of you've got some auto DR programs that are running. Some of the sites are subject to auto DR. And so what happens, you get these potentially huge imbalances in what's occurring. And trying to figure out how to address this, can be pretty challenging. But we do have some tools, tactics, and strategies that we can use. And again, this gets to the point of the analytics that are available to us. And so when we start talking about automizing distribution system operations, I referred to this a little bit earlier. So SCADA systems collect data on distribution system operations. They range from substation conditions to voltages and transformers or relays, and also they can ping and query intelligent electrical devices. So SCADA systems have been used by distribution engineers for quite a while now. They also SCADA systems enable remote and automated control of different distribution operations. So SCADA systems is a tool that most distribution system engineers are used to using. Advanced metering infrastructure, smart meters. This, again, I mentioned earlier that this collects a tremendous amount of information from endpoints, including voltage, current, reactive power, and energy consumption data. And AMI is, in some cases, you could be talking about thousands of smart meters that are collecting information, in some cases millions of endpoints. In addition, AMI includes solar meters, and so you can be collecting information on solar generation. At the same time, you're collecting information on demand at the site, so you get net consumption. And so that's increasingly important. When you begin to use AMI and SCADA in combination, what you can get is conservation voltage control systems. You can get volt bar optimization, where you're actually using capacity bank controllers and voltage regulation controllers to control operations within the grid. And so, again, there's some tools that exist out there, but we haven't really necessarily been using them in the way that can best help us. So I want to quickly go through some things that are done right now by utilities. So voltage monitoring is pretty common, and you can nowadays voltage monitor at multiple points and get a lot of information about what's occurring anywhere within your distribution system with voltages, whether that's, what's the condition relative to under or over voltage. You can look at time series and begin to look down into individual transformers to better understand what's the health of the voltage condition within the system. You can look at feeder voltage profiles and get a sense of what's happening with voltage over time at different branches and different distribution feeders. So you begin to get a more holistic picture of what's going on with the distribution system. AMI data helps us to understand programs better. So, for example, if we're looking at what's happening with customer load, so AMI allows us to dip down into hourly, 15-minute, down below that on certain instances, and we can compare customer loads to make decisions about what's happening with different customer segments and how are those customers responding to different programs. We also have the capability to use AMI to enable what we call technology analytics. And so if we begin looking at what happens with PV, for example, and we begin looking at how we combine weather forecast information with solar metering and AMI data, we can come up with ways to predict day, hourly, and nowadays more recently 5-minute ahead forecasts of PV output. That also allows us visualization of the dynamic of customer loads. And when we combine this with charging data, we don't get information just about individual sites, but also the collection of these sites within the distribution feeders. So you can imagine what could be happening if we combine solar output forecasts along with information on PHEV charging, distributed generation profiles, and demand reduction activities or programs. Again, AMI helps us to improve forecasting processes. So I mentioned earlier about the idea of improving our solar forecasting by tying this in with weather data. And again, we can use historical patterns of customer demand, again, by market segment and by different programs to actually improve our forecast processes. Here's an example of where we can look at not just, an hour ahead or a day ahead, but now we can look 7 days ahead, all the way roll this up to the substation. The importance here is, again, we're beginning to look at how we can treat individual sites, but more importantly, what type of information we get about how those individual sites as a collection might operate under different types of programs. This is really important when we start to think about how we want to combine programs together, or how we might want to treat distribution feeders as collections of devices. And so the other thing that becomes important is understanding system loads and the interaction between different customer classes and different loading within. In this particular case, we're looking at system load, but you can take this all the way down to distribution feeder loads. So the situation that we're now find ourselves in is we have a lot of information about grid loads, whether that's at the substation or feeder. We know a lot of information about traditional loads, and some of the inputs there include weather data, economics, end-use data. So that gives us a picture about what's happening with traditional loads. With solar metering and with some of the information that we have from AMI, we can get a very good idea about what's happening with what we call embedded solar, as well as other distributed generation. When we begin adding charge information from AMI, charging data, we begin to get a little bit better sense of how charging might influence a distribution feeder. And lastly, again, we look at existing programs like DR programs and what happens when we begin to layer DR programs on top of this. So again, now we're in the situation where we've got a lot of information available to us, and so how can we start using some of this information? So in order to stay away from what I call information overload, we need tactics and strategies. And so what I've put here is a very simplified distribution feeder type system, and we really want to adopt some tactics and strategies. So what I've done here is I've outlined some of the branches that are in gold would be branches that are subject to DR programs because perhaps they're highly congested, perhaps there are reliability issues. There's something about that branch that is of interest and causes a DR program. The green dots here, again, I've kept this fairly simple, these are PV systems that are known to have some minimal export. Most PV systems, by the way, will do net export throughout the year. Some do a lot more than others. So the red dots represent PV where net exporting is occurring quite a bit at the time during the year. It can be occurring at low demand times on distribution feeders. We've got load change tap regulators, voltage regulators. We might have different types of DG systems placed on this grid. And of course, here we have collector heads for AMI systems. So each of these systems might have, households would have AMI installed on them. Again, this is a very simplified diagram. We might be talking about in any distribution system, you could be talking about hundreds of homes, in larger, thousands of homes, commercial businesses, maybe each equipped with AMI. And so one of the things that we try to do, or we want to start doing, is we want to get a baseline of current conditions. So again, with our distribution system tools, AMI, SCADA, we can collect real-time data. We can look at what is the health of the feeder right now, at this minute in time, this moment in time. Is power flow good? Are power factors high? What about voltages along all of the branches? How much headroom is there in this distribution feeder? These are snapshots that provide us a baseline, but we also have to remember that this baseline is being updated all the time. We also want to look at near-term future conditions. So I'm talking about, an hour out, maybe 5 minutes out, but based on our forecasted information, again, using weather information, using program information, using AMI data, what events do we think might lead to a DR activity or cause a loss of power from a PV system? Again, weather conditions changing. So we begin to get a sense of what things might be happening in the near-term future. And then, again, longer-term future. So we might be thinking 2 days or 2 weeks out. And what types of conditions could occur that might cause problems in these distribution feeders. So by organizing these changes by time and looking at the ways in which combinations of changes can impact the distribution feeder, we can gain some insight on how we can develop tactics and strategies to deal with the changes. So one way to start thinking about this is we can begin looking at simulations of different types of effects. So here again, very simplified, what I call color crayon type charts of what's happening in a particular site when you have high demand, but there's no DR program. So you might expect, the peak to occur, going over what the expected peak is. That rolls up over many, many different sites to the feeder, and then within the feeder we can project out to the system. You might then also begin to simulate what's happening when demand response goes into effect. Okay, so again, you look at sites, you would then roll that up to the feeder and then beyond. And you can play the same type of simulation game looking at, so now let's look at sites where they have PV but they're not part of a DR program. So you get simulations of those types of sites, again, rolled up to the feeder. And you can look at what about when PV is, when we have sites where PV is predominantly exported out to the grid. And so, again, you begin to categorize this. So there's nothing really challenging about this other than it requires a lot of different type of data. And now what happens when you begin to add PV export and DR? So again, what we're trying to do here is find different combinations of these activities that can lead to problems. The idea is that we want to simulate these conditions, because if we can simulate these conditions, we can actually begin to develop algorithms that are useful in what type of control strategies we want to deploy. By the way, when I was talking about DR programs, this approach is very similar to what how DR algorithms are developed, so that, again, we can come up with auto DR type programs. So it's not a huge stretch to think about the idea that we can use these simulations to potentially come up with algorithms for controls that take into account these disparate types of activities within the distribution feeder. Now, being an AMI company, being a smart grid company, there's always the attractiveness of, well, we're going to meter everything and we will try to use all of that data to make decisions. Well, in actual fact, that's probably not a very good idea. You don't want to try to meter everything. In fact, what you really want to do is you're going to monitor that information that has the most importance to the grid conditions. And so you're not going to meter every point. You're going to meter points that, based on your simulations, are the ones that can be good indicators of changes. So that also takes you to the point that you don't want to just look at what's happening at that moment, but you want to use your data to look at trends. You want to see what types of incipient changes are occurring that are critical to the condition 5 minutes out, an hour out, maybe later. And so again, you want to tie your control algorithms that connect these trends to simulations. And so what we're really interested in doing here is, let's see, well, it wouldn't do it for me. Again, we want to, we're not going to meter all of these. We're going to use what we call bellwether metering. So just certain meters. And those can change depending on what types of information you're trying to collect. But you're going to do bellwether metering to collect critical information. Well, there we go. So again, you can think about the fact that you're collecting this information from just scattered types of meters, but they're organized in the ways in which you know based on your simulations that they're collecting important information. So I've covered this fairly rapidly. There's a lot of information in how this actually gets done. It's challenging, there's no doubt about it, but it can be done. And so some of the conclusions that we can draw from this information is the grid's changing rapidly. It's changing rapidly on a number of fronts, and that makes predicting the future very difficult. Consequently, it's important to have a methodology that's flexible and it doesn't rely on a specific set of outcomes. You can't guess what these outcomes are going to be. You can simulate things, but you really can't guess as to what the outcome will be. For a variety of reasons, we can expect to see continued growth in renewable and distributed energy systems. When I talked about the huge growth in PV, market experts have indicated that we can expect to see a fair amount of that come in as distributed renewables. What's really important here is that any solutions that we begin to take in hand for how we look at the grid in the future, it has to make renewables and distributed energy resources part of the solution. I mentioned earlier network systems. Network systems are really important because if we start to think about, we have a top-down grid for the most part in many parts of the country, and yet, you know, going back to the idea that central station facilities will provide all the electricity needs of customers probably won't work well. And not because I'm anti-central station. I actually think central station facilities make a lot of sense. But what's happening is we've got customers who want control. We're seeing that surface in many different arenas. They want control, they want certain things. Maybe that's green energy, maybe it's just, you know, a hedge against price volatility, but we're seeing greater and greater need to have distributed resources. If those become part of the system, then we have to find ways in which we can use them effectively. Network systems allow us to go to multiple generations. So if you think about things like, the old time, IBM would put a large mainframe computer at campuses, and that's how everybody used their computing power. To all of a sudden, everybody's got, laptops, they have iPads, they've got phones that are immensely more powerful than those mainframe computers. That's the kind of change that we see occurring, and we have to find some way to harness that. And so network distribution feeders enable us to do that better. Lastly, we really have to begin taking smart grid tools coupled with our analytics to come up with tactics and strategies. And again, I talk about tactics being the minute-to-minute, hour-to-hour types of approaches that we use with automated control of distribution feeders that take into account all of the different variety of DERs that we have out there. Strategies are things that we think about in days ahead, months ahead. It can even go out to what's happening to the marketplace over the next year or 2 years. And so we begin to think about how can we build out our networks? What type of AMI systems do we need? How do we develop these algorithms that allow us to better control these? So again, these analytics provide us a powerful means to addressing our rapidly evolving grid. And with that, I wanted to leave a little bit of time for questions, so I'm open to questions.
Great. Thank you so much, George. So, again, if you have questions, you can type them in the Q&A field down at the top left of your screen, And also, I think we'll go ahead and let people unmute themselves if you want to ask a question out loud. You can do so by pushing #6. George, you must have done such an excellent job of explaining it. There's no questions. Again, hit #6 if you'd like to ask a question out loud, or you can type in the Q&A tool. Okay, well, George, do you have any concluding thoughts or comments you'd like to make before we wrap up? Oh, we have one coming in here right when I said that. Here we go. How do you see statistical methods being woven into operations?
Okay, well, statistical methods, when we talk about solar forecasting, for example, we use statistical methods to improve our forecasting, so we're constantly looking, as we're developing, as we're using weather data, we're also going back and looking at, from a statistical perspective, we're looking at how well did those forecasts work in the past. And the past can be 5 minutes back, it can be an hour back, it can be 2 hours back in time. And so we're using statistical analysis in that reference frame to help us improve our forecast capability. And I expect more and more, I mean, anybody who's doing deep data diving on AMI data, statistical analysis is at the core of how do you make sense of all of the numbers. There's no way to really make sense of those numbers without that type of an approach. But I'm also, what I try to stress in this is it's not simply a question of statistical analysis. In the case of trying to figure out tactics in the near term, you really have to be looking at data where you're grabbing a strong trend. And again, statistical analysis can be very helpful as you're trying to figure out what is that trend and how fast is that rate of change occurring.
Great, thank you. All right, and then what about statistical methods in regard to phase identification?
I'm sorry, I missed the last part.
Statistical methods into phase identification?
Phase identification?
Correct.
So I guess I'm misunderstanding the question.
Okay, so the person who typed that in, could you maybe clarify, and I'll go on to the next question. This next question is, how much does the accuracy of the distribution grid connectivity affect the applications you are proposing, especially at the secondary part of the network where DG is connected?
So again, if we're thinking about, so one thing I would caution about is you definitely, anytime that we're dealing with tremendous volumes of data, again, hundreds of thousands, if not millions of endpoints, you're going to have certain data that you're going to have to dismiss, just bad data. But I wouldn't get caught up in too much of precision if you're trying to think about it from the perspective of trends. And so again, if you're talking about secondary systems, secondary distribution system directly to home, and we're talking about, how accurate is that data? Again, in the simulations, you're grouping things and you're beginning to look at what types of general trends occur. And I think at the end of the day, when we look out over the class of data, those trends are going to wash out some of the noise in the background. So accuracy is important, precision is important, but again, the overall context is what is the trend that's occurring? How can we classify these according to algorithms, and then using real-time data to always true up what you think is happening in your algorithm, what's happening in the next moment in time. So accuracy is important, but it's not an end to itself. Did you get clarification? Sure.
I did not. The person asked the question about statistical methods. Here we go. Here it is. How much does the ability of DGs to sell stored power to the grid complicate the load curve simulation approach?
So just like with PV, where we're talking about net export, so there's a lot of different complicating factors. So when I know in California, in certain cases, self-generators have been limited with their export out to the grid. I think that's in the process of changing. And again, the California Public Utilities Commission is looking at distributed energy resources planning, and that's one of the questions is, so how much should these generation systems be allowed to export out to the grid? And again, I look at it from the perspective of, what are you modeling? How does that fit into your category of simulations? And then what does that mean? So the simulations can become very complex, but again, what we're trying to figure out is brackets for, what would be a worst case scenario. If you start, so I tend to group things by what is the penetration of that? What's its capability to ramp into the grid? How much is controlled by that system? Can we set up, a way in which that can be controlled remotely, which is always a big question with distributed generation because the utilities don't necessarily want to take liability for that. So I don't see the utilities controlling those, but I do think that there will be methods by which those systems can be brought into the grid under certain regulations to provide power. It might be a bidding process. It might be some other means by which they can provide ancillary services. So again, the question was how complicated is it, and especially with respect to the statistical analysis. Again, it's complicated, but all of this stuff is complicated. And I think, again, the treatment is to try to put these things into groups and treat them as groups within simulations. Again, if you look at for example, how EPRI is handling hosting capability within PV, there's a lot of analogies to the idea that you can begin to use classification schemes to come up with ways to think about how do you want to respond to those changes. What does that particular technology, with its location within the grid and what it does, how does that change the dynamics?
Great, thank you. All right, another question is, what is roughly the solar panel energy conversion percentage of efficiency?
I'm sorry, the question is how efficient are PV panels?
Right, what is roughly the solar panel energy conversion percent efficiency? I think you're right, yes.
Well, cell efficiencies are getting fairly high. Panel efficiency, module efficiencies, if we're talking about any moment in time, so it depends on, if we're talking about clear sky conditions. Are you talking, so there's actual ratings of PV modules, so we can be looking at efficiencies, the efficiencies are going to vary from panel to panel. And I'm not a PV expert in terms of efficiencies nowadays, so I will beg off that question and pull in a PV expert. But they vary from, if you're looking at a clear day, you're looking at, over time, there's soiling effects. So if you're talking about a lab test versus a rating by what we call PVUSA test conditions, it varies. So there's not a single efficiency that I would feel comfortable telling you.
Okay. We have another question. Since you are talking about 5-minute measurements with the AMI, how are you dealing with diversity of the load or cycling loads such as heating and AC, and how do they affect these statistics?
So again, you have to put these into classification. So you begin to look at, well, in fact, we're looking in some cases at faster than 5 minutes. And so whenever you're talking about classifications of sites, you want to be talking about what's causing this change in the load. Certainly you can dive down into HVAC, but HVAC in itself is dependent on weather conditions. You want to see how frequently that's occurring. You want to understand, are there geographical specificities to this? So, for example, if you're in an inland condition, your HVAC load is going to be very different than in a coastal condition. So there's an attractiveness to dive down into what's causing that load change. And again, you want to be able to look at those factors, but from the perspective of, is this something that would be part of a DR program? Is this something that's not subject to DR? Is this something that I would expect to see for this category of sites? And how do those categories of sites fit within? Am I looking at branches, locations of those sites within branches that are heavily congested, or have reliability problems? So I want to link what's happening with that change in load to what might the effect be on the branch or the distribution feeder. So I don't want to get tied up in just looking at, this is due to lighting, this is due to HVAC. I'm going to instead worry about what's the impact. From my perspective, I'm going to be worried about what's the impact of that on a DR program, or if I see that that site also has PV with it, and is there going to be a relationship between something else happening, like cloud cover, unmasking my load at the same time that I've got a DR event occurring. I hope that makes sense. So again, I don't think it's helpful to jump down into the details when you're doing that type of approach. You need to understand you're going to classify it similar to how, from the perspective of a cause and effect, but looking at the breakdown into individual components, I would do that only to the extent it's going to help you with classification.
Okay, and we do have clarification on that one question with respect to statistical methods and phase identification. The clarification is this. For example, statistical methods might exploit AMI data to isolate a unique signature of a distribution feeder, and this kind of work has been proposed.
Well, absolutely. We use AMI data right now to look at individual transformers, and you definitely want to be able to tie your AMI data. You can think about to distribution feeders. And again, it goes back to the idea of getting a classification scheme of if your utility, one of the things you can use AMI for is getting a better understanding of what are the changing conditions within each of your distribution feeders. So you definitely want to have a connection between endpoints on the distribution feeder and tie it back to SCADA data that tells you about the condition of that feeder. It's that crossover that allows you right now to look at automated operations of distribution feeders. So if the question is, do we want to make sure that we're tying individual AMI to distribution feeders, the answer is yeah, absolutely.
Great, thank you, George. Okay, at this time there are no further questions. Any concluding comments that you'd like to make before we wrap up?
No, I think that's it for me. Again, I want to thank everybody for taking the time to join us on this webcast.
Wonderful. Thank you. Thank you, George, and thank you all for attending. And I did see another question about sharing the slides. We will send the PDF version of the slides out to everyone, and we will send a link to the recording as well that will be posted in the next couple of days. So stay tuned for that. And thank you again. We do have one other webcast taking place in this analytics series, and that is next month on March the 18th, I believe. So you should have received the invite for that as well. Thank you again, and please let George or I know if you have any questions. Thanks so much. Take care. Bye.